Hello everyone, welcome back to our subject Computer Organization and Architecture. So today we are going to move second unit, that is related to arithmetic operations. So here in the second unit we will be mainly focusing on analyzing the logical circuits involved in doing arithmetic operations like addition, subtraction, multiplication and division. So when we analyze, we will get to know the drawback of the drawback involved in designing the circuits and how to rectify that drawback. So how to improve the circuit design so that the performance gets improved. Okay, so we need to delay the operation time, and how to when we delay the operation time, definitely the performance of the computer system gets increased. Okay, so today the first topic we are going to see is addition and subtraction of signed numbers. Okay, so signed numbers in the sense both positive and negative. When we speak about unsigned numbers, it means only the positive numbers. Unsigned numbers are positive numbers. Signed numbers are both positive and negative. So before getting into the topic directly, so we need to know the basic knowledge on representing the signed numbers in computer system. So for this we have taken an example for 4-bit binary number. So as we have discussed in the previous class itself, if a word is a 4-bit, so it can accommodate 16 words, is it not? So 2 power 4 is equal to 2 into 2 into 2 into 2 is equal to 16. So if we store unsigned numbers, means we can it could range from 0 to 15. 0 to 15 is equal to totally 16 unsigned numbers. Then when we think of the signed numbers, means both positive and negative numbers. So out of 16 numbers, we will have 8 positive and 8 negative numbers, is it not? So how to represent all those things in the computer system? Okay, so just have a look on this table. So we have the 4-bit number, all the combinations are given, ranges from 0, 1, 1, 1. Okay, so from here to last digit, so 1 1 1 1. Okay, so totally 16 numbers are there. So we can represent in different ways. In this example I am showing you two ways alone. Okay, sign and magnitude representation of the number and 2's complement. So of course 1's complement is also there, but generally our modern computers will do 2's complement, addition and subtraction. So here today's topic we are going to see about addition and subtraction of signed numbers. So here take a look on this. So if the 4-bit digit is of 0 1 1 1, this is of plus 7, and this is 0 1 1 6 is 0 1 1 0 is plus 6. Likewise it goes up to all 4 0 means plus 0, and here the last bit, this part we will be saying as most significant bit, MSB, the leftmost, and the rightmost will be saying as LSB, least significant bit. So in signed numbers, the most significant bit is used to represent either positive or negative. Okay. If the MSB bit is of 0 means it indicates the positive number. See here, so these are all zeros. So that's what the in signed representation we have the positive. And if the MSB is of bit 1, so it is representing the negative number. So the MSB last most significant bits all are 1 here. So we have the representation in sign magnitude as minus 1, minus 0, minus 1 up to minus 7. Okay, so see here in sign magnitude we have both plus 0 and minus 0. Okay, so this is of no use, I think. So that's what the modern computers will prefer 2's complement implementation of signed numbers. think of it in 2's complement. So here these numbers, the positive numbers will be as it is the binary numbers. So all 4 zeros is 0. Then here 1 is three zeros, 1 is nothing but 1 2 3 up to 7, that is okay. And see here in 2's complement representation, so MSB is 1. So here 0 0 0 is -8, 0 0 1, I mean 1 0 0 1 is nothing but -1. Likewise it goes on, all 4 ones means -1 in 2's complement representation. Okay, so how so you have to get knowledge on 2's complement addition subtraction. Okay, so let me have a simple example. Just I'll convert how to convert a number. Okay, so if I give a number -7, so minus, and how to represent that -7 in 2's complement. So first we need to know about 1's complement. Okay, I'm trying to get okay here. So -7. So here, so how to represent -7? How -7 here gets 1 0 0 1? So okay, so for this we need to take +7. +7 is nothing but 0 1 1 1. This is +7. So to convert the given number into negative number, first you have to convert this into 1's complement and add 1. Okay, that's the way of getting 2's complement representation of a number. So the 1's complement is nothing, 1's complement of this +7 is nothing but change 1's to zeros and zeros to 1. That's it. Okay, so the 1 0 0. Okay, so this is nothing but 1's complement of 7, and after that we need to add 1. Okay, so add +1. So if we add, then we will get 0 plus 1 is 1 0 0 1. Okay, so this is the 2's complement representation of -7. See here, you could check it. So 1 0 0 1. So we could not remember all these negative numbers binary representation. So from positive number we could get it by taking the positive numbers binary representation and convert it into 2's complement by 2 steps. First is convert the given positive number into 1's complement and add 1 to it, so that is equal to the 2's complement representation of any number. Okay, so here this is -7. Okay, so with this little knowledge on binary number systems, we will move on to addition and subtraction of signed numbers. Okay, so here in this example we are going to add two numbers. Okay, so consider here in this table xi and yi. Okay, so in an n bit number, so at any stage I. Okay, so we are, so n bit in the sense, in this example for simplicity we take 4 bit. Okay, in the 4 bit at any stage of I. Okay, let's see what's happening. We will come to this example, then go to this table later part. So we are adding x plus y. So consider x is equal to 7 and y is equal to 6. So when we add, answer is 13 in decimal number. So what happens in binary representation? 7 is nothing but 0 1 1 1. 6 is nothing but 0 1 1 0. Okay, so when we add, initially least significant big, so this one here, no, so this is nothing but carry in, the carry comes in while addition. Okay, so then after addition the carry will come out, so that is represented here. Okay, so this is the way of representing when we add any two numbers at any ith stage. Carry in is denoted by Ci and carry out is denoted by Ci plus 1. So here initially carry is 0. So 0 plus 0 plus 1 is 1, and there is no carry. That's what here it is represented as 0. Then we add 0 plus 1 plus 1. Answer is 1 plus 1 is 10. Is it not in binary number system? We need to put the sum as 0 and it produces the carry. Since it is 10, 0 is the sum and 1 is the carry at this stage, and this will be the carry in for the next stage. So we have 3 ones. 1 plus 1 plus 1 is 11. 11 1 here 1 we are writing it in the sum and it carries 1. Okay, so then 1 plus 0 plus 0 is 1. So this is how the addition and taking place in a computer system. Okay, so now we'll get into this tabulation. Okay, so for different combinations since the three inputs are given, so xi, yi and carry also. Okay, so each and every stage we are adding three numbers, so one x, y and carry also. Okay, carry in from the previous stage. So three combinations means we will have totally 2 power 3. 2 power 3 is nothing but 2 into 2 into 2 is equal to 8 combinations we have. So for ranges from 0 0 0 to all ones. Okay, so these are the 8 combinations, and when we add all those things, what's the sum and carry? When we add all three zeros, sum and carry is 0. When we add all these numbers, sum is 1, carry is 0. And here similarly 0 plus 1 plus 1 is sum is 1, carry 0. And here if we add this 0 plus 1 plus 1, the result is 10. In 10, 0 is the sum and 1 is the carry. Similarly 1 0 0, here sum is 1 and carry. Likewise it goes on. So 1 plus 1 plus 1 is 11. So here sum is 1 and carry is also 1. Okay, so in this 3-bit input combinations, the sum when we get the sum, so the sum is nothing but, so we get sum in at four stages, is it not? So we have the sum 1 when xi is 0, yi is 0 and carry ci is 1. Okay, so that is represented here in this manner. Okay, xi bar means 0. Okay, so xi bar, yi bar, ci, that means 0 0 1. Then when we get here xi bar, yi, ci bar. Okay, so xi bar means 0, yi is 1 and ci bar is 0. Similarly when here xi, yi bar, ci bar. Okay, plus xi, yi, ci. So only in this 4 combinations we get the sum as 1. Okay, so this is simply nothing but XOR combinations. Okay, so this plus this whole circle is represented by the symbol XOR. Okay, XOR addition, I think you will be knowing the truth table. Okay, let me recollect it for that truth table of XOR. Okay, so when we have 0 0, the output of the XOR is 0. Okay, so when we have truth table 0 1, the output of the XOR is 1. When we have 1 0, the output is nothing but 1. When we have 1 1, the output is nothing but 0 in XOR. Okay, so this is the truth table for XOR logic circuit, and here for the 3 inputs, this is the combinations it gets produced. And I will move on to this carry. Okay, so carry out, when the carry is produced when we have these combinations, xi ci is 1, xi ci plus means OR operations. Okay, then we have xi yi ci, xi ci, then we have xi yi. Okay, so only using the two inputs we could predict the carry out. So this is the equation to produce the carry out. Okay, so at any stage I, so I represent at any stage, so this is the sum at this stage, and what's that carry for the next stage is represented by ci plus 1. Okay, I hope you are following with me. Please pay close attention. So we are going to discuss about the logic circuits involved in this addition. Okay, so here comes we got two equations. So one equation for the sum and the other equation for the carry. Okay, for the sum it's enough to have 3 input XOR logic gate. Okay, so that's what the XOR logic gate is represented here. So this is the symbol for XOR logic gate, which takes 3 inputs and produce the sum. And for the carry, what's the carry equation? So we need 3 and gate and 2 OR gate. Okay, so plus indicates the OR gate, and here XI this is AND operation. Okay, so we need 3 AND gate and 1 OR gate. So 2 OR gates, but all the 3 input, all the 3 and 3 is and value is given in the one OR gate itself. Okay, so 3 and we need XICI, YICI and XIYI. So all are AND operation, and the result is given to OR gate, and there it produces the carry. So this is the basic logic gate for designing the sum and carry of adding two signed numbers. So here please concentrate, we are discussing about the signed numbers. Signed numbers means which includes both positive and negative. Okay, so this, for simplicity, this logic two circuits, sum and carry, is combined to produce an one logic circuit called as full adder. Okay, so this is the symbol for the complete circuit of this operations. Okay, full adder. So it takes 3 inputs and produce 2 outputs, sum and the carry out for the next stage. Okay, so this this complete 2 circuits we are making it as a full adder. So full adder, there are adders like half adder, full adder. So full adder will take 3 inputs and produce 2 outputs, whereas half adder means it takes 2 input and produce 2 output as carry and sum. So here full adder. Okay, and coming this that is for carrying out carrying out the addition or subtraction operation at any stage I. Okay, suppose if I have 4-bit number. Okay, so 4-bit 4-bit number, I need 4 full adders. Okay, so that's what we have here, n number of full adders for n digit addition operation. Okay, so here this is the logic circuit to carry out the n bit addition. Okay, so this logic circuit we are saying as an n bit ripple carry adder, because in each and every full adder it will produce the carry out that will be given as an input to the another full adder, and that will perform the addition operation, and which again produce the carry out. It propagates to each and every stage, is it not? So that's what we are saying this adder as an propagate or ripple. Okay, so cascade and full adder blocks to form an n bit adder. Cascading means, so n numbers. Okay, we are performing addition for n bits. Okay, so the, only one bit addition will be performed by one full adder. So for n bit addition we need n full adders. Okay, so the carry, since the carry propagate or ripples through this each and every stage, we are saying this arrangement has nothing but n bit ripple carry adder. Okay, so I hope you are following with me. It's quite simple. So full adder means it will take 3 input and produce 2 output, and the one output is the sum, the other is the carry, which is given as an input to the the next full adder. So the carry is propagated or rippled to next full adder. That's what this combination we are saying as an n bit ripple carry adder. Okay, so here this is the least significant bit, and this one is the most significant bit. Okay, so most significant bit only we will get to know whether that number is positive or negative. So if MSB's value is 0, that number is what? Yes, of course you are right, positive. And if MSB bit is 1, that is of course a negative number. And let's see the circuit arrangement for kn bit adder. Kn bit means, for example, if I have 4-bit adder. Okay, what happens if I want to add a 16-bit 2 digits number? So it means I need 4 4-bit adders, is it not? Each adder will perform 4 bits. So 4 plus 4 plus 4 plus 4 is equal to 16, is it not? So that's what it is represented as kn bit adder. Okay, so this is one set of 4 bit adder, the other set of 4 bit adder. So totally all combined to give me an answer for kn bit adder. Okay, so here kn bit numbers can be added by cascading kn bit adders. Okay, so I think you are following with me. The previous diagram is for n bit adder. Okay, so n bit, for example, if you take 4 bit means this will perform only 4 bit addition, okay, of two numbers. So here we could expand that 4 bit to 16 bit. So 16 bit means we need 4 bit adders. So that's what here that k represent that 16 bit means we need 4 bit adders. Okay, and here one more thing, the carry in C0 in the LSB plays an convenient way to perform subtraction. So here one point is given, please make a note. The C0 in the LSB provides a convenient way to perform subtraction. So here, so I will come to this point. So here this entire circuit arrangement will do both addition and subtraction. Okay, so as I told you, for subtraction it is done by 2's complement representation. So for 2's complement, given number has to be converted into 1's complement, then we have to add 1, is it not? So for adding that 1, this bit C0 will play a big role. Okay, so I'll come to this concept in the next slide, and just keep in mind that part alone. So this plays a major role in doing 2's complement addition or subtraction. Each n bit adder forms a block. So this is called as a cascading of blocks. Okay, so each n bit forms, this is one block, this is one block, and it ripples to next stage. So that's what this arrangement of is said to be cascading of blocks, and it carries the carry is taken to each and every next blocks. That's what this is said to be blocked ripple carry adder. Okay, the adder will perform 4 bit a 4 bit adder forms a block. Okay, and it will produce the carry is propagated to the next block. So this arrangement we are saying as a blocked ripple carry adder. Okay, I think it's quite easy for you. Let me explain here also the input and the output. So here n bit, no, so n bit in the sense 0, it will take 3 inputs. So one is carry and the other is 2 inputs x and y, each is of n bit. So y0 to yn minus 1, since it's starting from 0, it should end with n minus 1. So totally n bit. So x0 up to xn. So then it will produce the carry as not cn minus 1. It will produce cn. Okay. So if it is of we have seen in the previous slide itself, carry out will be ci plus 1 at any stage. So here n minus 1 is the MSB, and it will produce the carry as cn. Okay, that is given as an input to the next set of block. Likewise it goes on, and these are its respective what sum. Okay, and final stage we will have the carry out. Okay. And coming to the binary addition subtraction logic circuit, so the complete logic circuit to carry out both addition and subtraction operation. Okay, so this is the arrangement of the adder, full adder. So let's see, it will do both addition and subtraction. So as I told you, addition means just the binary representation of that number, but for subtraction what we will do, we generally subtraction is nothing but, so here it is given here. So x minus y is a subtraction. This x minus y, this is nothing but adding 2's complement of x to y. Okay, so take 2's complement of y and add it to x. Okay, so normally we are performing addition operation, but before that we are converting something that given number y, the minus y. Okay, minus y as 2's complement representation we are making it, then performing the addition. So 2's complement is equivalent to, as I said, take the given numbers 1's complement and add it to 1. Okay, so x minus 1 is equal to x plus y bar. I think here that bar is missing. Let me correct it. Y bar means complement of y, then plus 1. Okay, so basically we are performing addition, is it not? So here adding. That's it. Okay, so if we have the number negative number, so we need to perform 2's complement. This logic circuit performs the 2's complement using by implementing that XOR by passing the by passing the second value in XOR gate. So see here there is one control called as add subtract control. Okay, so this what this control says is, when we perform addition operation, give its input value to all the XOR gates as 0. So when we pass the value y, so it will be taken as it is. For example, if we perform 7 plus 1, I mean simple addition, 2 plus 3. Okay, so let me convert it into pencil. Okay, so 2 plus 3. Okay, so 2 is nothing but, so x value I am passing it in x value as 2 and y value as 3. Okay, when I perform addition, what's happening? So 0 plus 1 is 1, 1 plus 1 is 0, and it produces the carry 1. So 1 plus 0 plus 0 is 1 and 0, is it not? So this is 5. 2 plus 3 is 5. Okay, so when I pass, this is x and this is y, so when I pass this y value, what's happening? So in the controls, in this control I am giving I am performing addition operation, so its value will be 0. Okay, so all values will be 0. So 0 here, so this is 3 value now. So number 3 is represented as 0 0 1 1, so its LSB is 1, so that's nothing but y naught. Y naught is 1 and 0. So 0 1 passes through XOR means its output is as it is 1. Here 0 1 is 1, 0 0 is given to XOR means its output is also 0. So the same value is passed, 0 0 1 1 will be passed, and here in x value 0 0 1 0 will be passed and performs the addition, will be getting it the output, and of course the carry C naught is also 0 when we perform addition. Now take an example for subtraction. So subtraction for what? 3 minus 1. Okay, so I am doing subtraction for 3 minus 1. So 3 is nothing but sorry, I will do it here. Let me convert it into pencil. 0 0 1 1 is what? 3. Okay, 1, then 1 is nothing but what? I will put it here. 1 is nothing but, in 4-bit representation, this is nothing but 1. Okay, so I am doing now 3 minus 1. So this is plus 1. I need to convert this into minus 1. So how we will be converting it? So here this control signal will pass the value as 1 here and carry also 1. So when we pass the all ones to all this XOR gate means this 1 will be converted into 1's complement, and C naught if the C naught value is 1 means it will perform 1's complement plus 1, so that is equal to 2's complement. Okay, so here all bits are 1 1 1 now, and I am passing 1 y naught as 0. Okay, so 0 0 and I mean 1, so y naught is 1, and here the subtract control is 1. 1 1 will produce me as what in XOR? So 1 1 is 0. Okay, then here 0 1, is it not? 0 1 is 1. Similarly for 0 1 0 1. So this is the 1's complement for this number. Then here we need to perform 1's complement. We need to add 1 to the 1's complement to get the numbers 2's complement value. So here the carry we are passing 1 value. Okay, so 1. If we do addition, what will happen? 0 plus 1 is 1, 1, 1, 1. Okay, so this is the this is the minus 1. Okay, so this is the 2's complement representation of minus 1. So we'll go back to the first slide and we'll check what's that. Okay, see here, minus 1 is nothing but all 4 ones. Okay, so in this way this logic circuit will perform both addition and subtraction operation. So hope you are all following with me, and this is quite simple, very simple arrangement. So don't get frightened at the very first time. If you used to practice this one, it will be quite familiar for you. Okay, such a simple logic is applied here. And there one more thing, finally I need to discuss about the overflow. Overflow occurs, for example, in a 4-bit number, we could the numbers will be ranged from, as I said, plus 7 to minus 8, is it not? So what happens if I perform 7 plus 1 addition? Is it not? So 7 plus 1 is 8, but that 8 is nothing but positive number. That positive number I can't store it in 4-bit representation. Then there comes the concept called as overflow. Okay, so overflow occurs when the sign of the two operand is the same. Okay, so let me take you to the first slide and repeat it again. So here what happens if I add 7 plus 1, I will get plus 8, is it not? But there is no plus 8 representation in this 4-bit combination. So the circuit doesn't able to hold that plus 8. So that's the thing, overflow occurs. Similarly, minus 7 minus 6 is what? Minus 13. There is no minus 13 representation in this 4-bit combination, is it not? So that's the concept of overflowing. So when we add the numbers, when both the numbers are of same sign, when plus 7 plus 1 is same positive numbers, 8. So likewise minus 7 minus 6 is equal to minus 13. Both the numbers are same sign. So in this situation overflow occurs, or when overflow occurs, the sign bit the resultant sign bit gets varied. Okay, overflow occurs if the sign of the result is different from the sign of the operands. At the last stage. So here, so we are speaking about the last stage. Okay, there is a way to detect that overflow. The circuit to detect an overflow can be implemented using this XOR operations. Okay, so what's happening? So when we need to think about the last bit, MSB bit. Okay, when the two values, X and Y values, MSB is 0 0, and the output is 1, or when both the input values MSB is 1 1 and the output is what's it here, bar means 0 0, so 0 0 1. So this is the output, is it not? So there comes the overflow concept. The sign bit gets varied. How to produce? Let me take an example. Okay, again I'll change it. Okay, plus 7 is equal to, in binary representation, this is equal to 0 1 1 1, and plus 1 is equal to 0 0 0 0 1. When I add, what's happening? 1 plus 1 0, carry is given. 1 plus 1 0, it takes the carry. Then 1 plus 1 0, have the carry, and 1 plus 1 plus 0 plus 0, here 1. See here, so this is 1 0 0 0. So this is not a plus 8 number. Okay, so here the both the sign bits of the input is same and the resultant sign bit is changed. So that's the meaning here given here. Overflow occurs if the sign of the result is different from the sign of the operands. Okay, over here if we have 1 1 and the result is resultant bit is 0, means also the this answer is wrong. Okay, so overflow occurs, it means the overflow occurs, we don't have that much circuitry designed to accommodate this value, that's the meaning of it. So that can be rectified by this equation. Okay, this equation is nothing but XOR operation of carry n and carry n minus 1. This we could implement it in the in this circuit. Okay, so in this circuit we could add that logic to check the overflow condition also. Okay, that's it about today's topic. Hope you have followed it, and it's quite simple. Okay, addition and subtraction of signed numbers. Okay, we have seen about full adder at full adder concept for 1 bit. Okay, so full adder will do 1 bit addition and subtraction. Okay, which takes 3 inputs and gives 2 outputs as sum and carry. And we have seen about n bit ripple carry adder, k n bit adder, then followed by the complete logic circuit to carry out the binary addition and subtraction along with deducting the overflow concept. So hope you get the overflow concept. Overflow concept occurs when we have when we add two numbers of same sign bit and the resultant sign bit is varied, then overflow occurs. That could be deducted that could be deducted and implemented using the XOR operation of this carry in of current carry in of previous carry in and current carry in. Okay, so with this our topic is over. I will meet you in the next topic. Till then, thank you all.